Okay. Okay, thank you for joining us this afternoon for the webinar with HPE on the new machine learning development environment. We will be recording this and posting it on our YouTube channel, so anyone misses it, they can still catch up with it. So just as a brief introduction, Comnetco is hosting this. We're partners with HPE. We've been involved with technical computing for a little bit over 20 years, and we've got experience with HPC, visualization, supercomputing, and knowledge discovery. We have been awarded a number of systems on the top 500, and including a dedicated AI research and development supercomputer. So here are today's speakers. Evan Sparks, who is VP of AI and High Performance Computing at HPE. Prior to, Evan was CEO and co-founder of Determined AI, which HPE acquired. Also, Phan leads the solution engineering team as part of the Artificial Intelligence Strategy and Solutions Group at HPE, also previously with Determined AI. So on that note, I'll turn it over to Evan, and we'll change our screens.
Great. Well, thank you for the introductions, and really my pleasure to be speaking with you all today about the HPE machine learning development environment. And thanks to the folks at Comnetco for organizing this event. It's always exciting to speak with, to be working with such valuable partners, and also to be speaking with some customers here. So today I'm going to tell you a little bit more about our HPE's investment in the HPE machine learning development environment, which perhaps no surprise is based on the technology that we acquired as part of the Determined AI acquisition last year. And so Determined AI made and continues to make an open source platform for large scale deep learning model training. And the machine learning development environment is the commercial instantiation of that software platform. And so particularly for this audience, I just wanted to kind of make sure that people understand that the strong connection between an open source project, which we continue to invest in heavily, and the commercial offering is there. As HPE, we're able to deliver not just software support and feature prioritization, but also highly designed systems in connection with partners like Comnetco to our customers who are building these AI models at scale. And so we'll talk a little bit more about that, but most of what I wanted to focus today on is really the underlying technology and the benefits that we bring to customers who adopt the machine learning development environment. And then in sort of the back half of this presentation, Hoang is going to show you a live demo of the technology, and it'll give you a good sense of, at least for a particular use case, what some of the benefits might be. But we find that these benefits are being mapped to users in a lot of different verticals. So we can go on to the next slide, and we'll get into it. So the high-level reason why we created the machine learning development environment is the following. So first, you have this beautiful sort of theory, which is that we have we've seen a step change in AI technology in the last several years, which says, hey, this deep learning stuff, advanced models powered by deep learning or other recent advances in machine learning is creating absolutely transformative applications. Cars that drive themselves, voice interfaces that actually work. Just want to make sure that the sound is coming through clearly. So voice interfaces that actually work, real advances in natural language processing technology. We're seeing it applied in everything from predicting the weather to other scientific advances in things like drug discovery. And we'll talk through some of our customer use cases in a little bit. But the theory is that, okay, apply machine learning to my problem and some transformative application is going to come out. And what we're seeing in practice, if we go to the next slide, is that actually, for a bunch of reasons that I'll detail in a minute, it's not just go apply this new technology by itself. It's that you need specialized infrastructure, not just hardware infrastructure in the form of, say, GPUs or other types of compute accelerators, but also software infrastructure to help organizations actually realize these transformative applications and build them. And so why is this? And that's the next sort of question I want to answer on the next slide. And that is that fundamentally, developing software that's powered by AI, powered by machine learning, is a different practice than developing kind of conventional software. Conventional software, you write down the spec, you implement a bunch of if-else statements, you write a few for loops, and you're done. Obviously, I'm undercharacterizing the complexity involved in software engineering, but that is the mindset of sort of what we think of as software 1.0. Software 2.0 is what we think of as applications that are powered by machine learning and powered by AI, and that is data is a first-class input. You're talking about data as the fuel for building and training these models. That data could be collected from sensors, it could be synthetic, it could be all kinds of things, but data tends to be at the kind of heart and soul of these AI-powered applications. The computational requirements for building these applications is orders of magnitude higher than traditional software development. GPUs, other advanced accelerators that are coming on the market, they produce, we're measuring the effectiveness or our speed to model in terms of flops and kind of supercomputing terms, which is a huge difference from classical software engineering. Even the definition of correctness is different, right? You talk to a machine learning engineer about how their model is doing, and they'll throw up a convergence plot, and they'll start talking in terms of probabilistic metrics that are measuring the accuracy of their applications, rather than, hey, are all my unit tests passed? And so these are some of the sort of the key differences between that classical software engineering and what we think of as software 2.0. And where we start to see problems really come in as we go to the next slide is that, not on what we think of in this slide as day one of model development. Day one of machine learning engineering has gotten pretty good over the last 5 years. That is, I, as a machine learning engineer, can go get my hands on a laptop or a desktop that has a GPU in it. I can pip install PyTorch or TensorFlow. I can go read a tutorial about how to build the latest digit classification model or something like that. And I can get going. And as long as things are sort of small and simple, it fits on one machine. I don't really have a team to share my results with. I don't really have infrastructure to manage. Things are actually pretty good. Yeah, I'm getting away with tricks around how I track my experiments, but it's okay at this level. Where we see challenges start to come in, it really, as on the next slide, as we think of moving to day two of machine learning engineering. That is, I have multiple users. That is, deep learning and machine learning becomes a team sport. So multiple users trying to collaborate with one another. They might be using different frameworks. They might be using, one user might be using TensorFlow, the other might be using PyTorch, etc. And they're both collaborating on underlying hardware resources, but they're also, in some sense, competing over those underlying hardware resources. That is, they need a way to share a large GPU cluster, say, to get their work done. They need ways to, software infrastructure, in our view, to collaborate on the experiments that they're running and make progress together towards common shared goals. And they need facilities that can help them take advantage of that whole cluster via things like distributed training and automate their workflows via some hyperparameter optimization. And so these are sort of the challenges that these users might face, in our opinion. Now, if we go to the next slide, one thing I want to call out is we're not the only the only people to realize this, right? The Googles and Microsofts and Facebooks and Nvidias of the world have realized that their users or their teams that are developing these kinds of AI solutions internally are often, need software infrastructure to be productive. They build out teams that build things like TensorFlow and PyTorch that the rest of the community could use. But they also have massive investment in internal software platforms to make these teams productive that aren't available to everyone else. And so the rest of the world is left piecing together software infrastructure and hardware infrastructure for AI that is based on, in the software world, open source tools, bash scripts, and duct tape, and oftentimes leading to a lot of maintenance of that software infrastructure that teams are building and maintaining themselves, as well as a lot of people reinventing the wheel. And so our goal at Determined AI and now within HPE is very much to provide a world-class software infrastructure for large-scale model development. And the way that is manifested is, again, in this machine learning development environment. So I won't, in terms of some of the key benefits, we'll talk about that in a little bit. But the way I think about the machine learning development environment is it is a system that sits between the end users and the code that they're writing in frameworks like TensorFlow and PyTorch to build their deep learning models. And it provides a set of services that helps accelerate this model development through advanced hardware orchestration and resource management, and provides essentially power tools for these users to get leverage out of that large-scale hardware infrastructure that their organizations have invested in. So lets them use lots of accelerators at the same time to train a single model in the case of distributed training, automates a bunch of their work around hyperparameter optimization and neural architecture search, and provides facilities for reproducibility, for sharing, for experiment tracking, and so on. The entire platform is containerized, so everything that runs the system itself, as well as the user code, runs in containers that are a fundamental unit of reproducibility in our world. It can run on premise, so and we'll show you some of the sort of on-prem hardware that we can make available to customers. But it also runs just as well on the cloud. So we have customers running the software stack on places like AWS and GCP and Azure, and we have facilities that make elastically scaling the cloud portion of their resources really, really seamless. Now, as important as what the system does in this slide, which is the focus on facilities for model development and training, is what it doesn't do. So in the green boxes here on the left, kind of data acquisition and preparation, the ETL, and getting your data ready to do machine learning on it, we don't focus on that. We integrate with the top tools in the space, and we have users using everything from Spark jobs to more classical batch ETL jobs to Airflow and everything in between to get their data sort of ready and as part of a production pipeline for building these machine learning models. Similarly, we don't do really anything to facilitate model serving today, other than we have some facilities for batch inference, and we provide a model registry, which is a version data store or version model storage system that serves the model artifacts for consumption in downstream services. So we think of the output of our system as deployable model artifacts that can be used by downstream serving systems, whether that's serving systems that are running like in a self-driving car or running in a web service for things like fraud prediction and so on. And so that's kind of high-level overview of the system and kind of what it does. I want to talk a little bit about some of the quantifiable benefits of the system in the next slide. And where kind of these benefits come from. So first is around hyperparameter optimization and neural architecture search. So our team has been working at the bleeding edge of hyperparameter optimization and neural architecture search research for the last several years. And my co-founder, Amit Talwalkar, is a professor in computer science in the machine learning department at Carnegie Mellon, and this has been a central area for his and his students' research, many of whom are now staff members here at HPE. So we have bleeding edge algorithms based on asynchronous successive halving algorithms based on things like hyperband that do what we think of as principled early stopping that has been proven over and over again in both experimentally and theoretically in widely published academic research to be significantly faster, particularly in resource-constrained environments like we have when we're dealing with high-dimensional search spaces and deep learning, to be faster than existing methods. And so we have customers that start by saying, yeah, I could never have hoped to do significant hyperparameter tuning because training a single model is just too expensive for me. And they find that for the budget of training, collectively, say 10 models, they can explore hundreds or even thousands of model configurations in the same kind of resource budget and get dramatically better kind of accuracy out of the models at the end of the day. So that's sort of one pillar of tangible benefit that we see users getting. And I think as important as anything, the algorithms and so on, is just how tightly integrated this is with the system. The scheduler understands the difference between a hyperparameter tuning job and a distributed training job, for example, and understands the semantics of those jobs and where work can be moved around, what can be deprioritized, and so on. And some of this is based on kind of user configuration. But a common theme or a common pattern that we see with customers is they'll have high priority models that absolutely need to get trained in the next 24 hours because they're pushing them the latest and greatest out to their production systems. But then in the background, they might have a low priority task that's leveraging unused cluster resources to do things like hyperparameter optimization and making steady progress towards the goals of getting sort of more accurate models out. So that's the hyperparameter optimization kind of benefit. The second benefit I want to spend a little bit of time on here is distributed training. And so this slide is a little bit out of date because for a couple of reasons that I'll get into. So one is, so when we think about distributed training, what's the key thing that our users want to solve? Well, I want to go from a model that takes however many days or sometimes weeks to train on a single GPU, and I need that model to train faster. And I'm willing to throw more hardware at the problem in order to do this. So I want to go from training on one GPU to training on, say, 64 or 128 or more GPUs. And I want, ideally, in a perfect world, if I throw 100 GPUs at the problem, my model training is going to get 100 times faster. There's a bunch of reasons why that never works, unfortunately. It's never the case that 100 times more resources give you the 100x speed up. Gene Amdahl can probably profess on why that is. That's a little bit of a joke. But the gold standard would be linear scaling for these kinds of things. We actually see quite close to linear scaling, so 70 or 80% of linear, up to hundreds of GPUs on several classes of real-world model and NLP and computer vision, which is great. It means that if I throw 100 GPUs at a problem, I might get a 77 times speed up, for example. We do this through a combination of strategies, and this is where the slide is a little bit out of date. So, when we were doing the benchmarking that was shown here, we were actually building it on a variant of data parallel distributed training based on Horovod. And we included a bunch of optimizations in kind of our data parallel training strategies that reduce communication overhead and help drive that near linear scaling that you're seeing on the slide. Now, that's a moment in time and a time where we then said, okay, first let's give back these improvements to the open source community, and we've become members of the Horovod Technical Steering Committee and donated our improvements to that broader open source project. But we didn't stop there. We started to say, okay, what are the other avenues for improving on distributed training? And we've moved to a model where we're, as an option for users, allowing users to do 3D parallelism, which is taking advantage not just of data parallelism, but also for models that could grow really big, sharding models across multiple computers in a cluster, and doing that in a data efficient way. There's also pipeline parallelism, which is sort of the third dimension here. And so all of that is available to users. And again, in the context of from an end user's perspective, I don't want to have data scientists worrying about what are the ways that I might parallelize my model to train it on a large GPU cluster. Instead, what I want to give them is tools that say, I want to train this model faster. I'm willing to budget an additional N GPUs for the problem. And the system should go ahead and figure out what the right way to parallelize is. And as you'll see in the demonstration in a moment, that's exactly the user experience that we've been able to deliver with the machine learning development environment. And then the last kind of component of value that we really focus on with the development environment is providing tools for teams of machine learning engineers. That is, machine learning engineering has become a team sport. And unfortunately, the facilities for sharing the progress that researchers are making are often really brittle. You ask any academic researcher what it takes to reproduce a paper that they've read at the latest conference, and they'll say, give me 3 weeks, a bunch of pots of coffee, and hopefully I can get something that's close to what I see out in the state of the art with research. And this is not unique to research or academic research. It's something that we're seeing in industry as well. Even within teams, sometimes it can be difficult for one team member to reproduce their other team member's research. And this isn't because of bad incentives or bad acting or anything. It's because of a lack of tools. And so what we've tried to build the machine learning development environment to do really since day one is allow reproducibility and sharing to be a first-class concept within the system. And so I mentioned the Docker containers earlier as a unit of beginning to provide reproducibility. It's a maybe a necessary but not sufficient condition for providing that reproducibility. But we track everything that's running in the system, down to the random seeds that are often initializing the model weights, for example. And by providing those tools to track and reproduce these experiments, we find it much easier for teams to focus on their modeling and not on reproducing my colleagues' results or maintaining that underlying infrastructure. And so our goal is and it's been successful with a number of customers in the market, is really to help users focus on their modeling and not so much that underlying infrastructure. And we're seeing real improvements in team productivity. So I wanted to take just a few more minutes and talk through a couple of first, I mentioned sort of the hardware and software components that we're able to assemble together in kind of complete solutions that we provide to customers. And then we'll talk through how some of our customers are using either the software and the hardware that we're able to provide together. And so what I'm showing here is what we call the standard small HPE Cray AI development system. And so this solution is based on the Apollo 6500 server line and InfiniBand switching technology and interconnect technology. And we've purpose-built and designed this system, one, to be scalable, and so to be available in scalable units. So the system you're seeing right here has 32 GPUs in it, 32 A100 GPUs in it, but that can be expanded up to hundreds or even thousands of GPUs, as we'll see with some of the customer reference we'll show in a moment. It includes the hardware that's required for advanced AI model development. So again, this is a small version of the system that can expand out completely, but also the software stack. So cluster management software provided by HPE, the machine learning development environment is pre-installed. It comes available turnkey. We provide training for customers that are using the solution, and really the idea is that this is an appliance that for large-scale model training and research, designed for teams of tens to hundreds of machine learning engineers who want to share this hardware simultaneously and make use of the software that we provide to get their work done. And so that's a combined hardware and software offering. We actually just announced this offering last week, but we have some customers already using it that I'll share with you on the next slide.
Evan, if I could just jump in, I see on that previous slide the HPFSS. So for folks that don't know, HPE announced a partnership with IBM, and we're delivering the erasure code edition of Spectrum Scale today, and that's very conducive with AI workflows. So I see that there's four of those in there, and that's basically one recovery group, correct?
Yep, absolutely. That's a great point. So absolutely, you know, I focused a lot on the compute and the networking kind of portion of this, and those are the core of the offering. But for a lot of customers, they really want Spectrum Scale and PFFS as an option for storing, as a high performance option for storing their training data, and also perhaps their checkpoint data and the other intermediate data that they produce as part of their AI models. And so that's an optional component here. It's in this diagram and version of the system. It's a fully supported offering, and that to me marries the best of hardware, of compute, storage, and kind of data in one box. You can take it or leave it. So we're happy to work with customers on configuring the systems to meet their needs. Some customers may already have such a system in place, to your point, and already be using the advanced erasure coding features of this high performance storage system, and they may, you know, just need to have the computing networking added to them. We'll work with customers and be flexible in that regard.
Great.
So let's talk about a beta customer who is using this solution at scale. So as I mentioned, it's scalable. And the last slide I showed you was a 32 GPU configuration. This customer is running production today on a 512 GPU configuration and growing. And they are a large NLP research group based in Europe. So they wanted an on-prem solution for a variety of reasons. Combination of economics, knowing and trusting HPE for a very long time, knowing that we can deliver high performance solutions to these kinds of problems, but also the data that they're dealing with is sovereign, and they wanted to make sure that it stayed local to where they're doing their computation for regulatory reasons. And so we delivered to them a Cray AI development system, which is what we called it at the time. It's now called the Machine Learning Development System, that was purpose-built and designed for their large-scale natural language model training. So they're training really big language models. You've probably heard of things like GPT-3 as an example of a large-scale language model. So it is models like that. They're not exactly that, because this customer needs to customize the models to match their particular data sets, the languages that they're modeling, et cetera. And they're pushing forward the cutting edge of research in this space. So they're doing multimodal training and so on. And so for them, the benefit was, once the system was delivered, they were able to get up and running using 3D parallel model training, which I alluded to a little bit ago, which is necessary to train these large language models really out of the gate without many code changes at all. They were able to see benefits of this 3D parallelism, and we worked with them closely to tune the hardware, but also the software configuration to match their workload and really maximize throughput and performance. And that's one of the things that we do as part of professional services engagements with customers as we're driving these models to scale. And so they were able to see significant improvements in that training throughput by virtue of sort of this engagement. And you know, we continue to work closely with them to make sure that, one, the models they're working on today are still performant in the system, and of course they are, but also to look forward as they're looking at the next, you know, order of magnitude in terms of data that they're going to be training these models on, or fundamental changes to the workload, making sure that the entirety of the solution, the software and the hardware together, are designed to meet their requirements. And so it's really exciting, and we're excited to be working with this customer. And it came out last week. Their name is Aleph Alpha, and they're based in Germany. The next customer I wanted to talk about is kind of pertinent to some of the folks in this audience, and that is a customer that's in more the government space. And so this is a large defense contractor that is working on-prem hardware, not necessarily HPE hardware, but is working on developing large-scale models using the underlying GPU technology, but leveraging the machine learning development environment as their software stack that sits on top of this. And so we'll work with customers wherever they are, based on their hardware, particularly if that hardware is designed for large scale AI models. And so this customer had an option. They had a buy versus build decision, right? They could have built a complete stack for themselves based on open source technologies. And they're doing that for certain portions of their platform. But because we have an open source core based on the determined training platform here, for workloads that need to be completely based on open source technology, they'll use that. But for workloads where they want commercial support, where they want our services in helping scale, and where they want advanced security features, they turn to the machine learning development environment to garner these features. And as a result, when they were at small scale, say a dozen GPUs or so, they were fine with just running sort of the open source technology. But as they got to an enterprise scale and needed commercial support, needed feature prioritization, and so on, that's when they began leaning on us. And so we've been working with this customer for quite a while now, and powering their users who are doing some of the most advanced defense-related kind of AI projects here. We can go to the next slide, and we'll talk about one that's a little bit more in the realm of scientific research, because I also know that that's relevant to this audience. And so this is a privately held or a publicly traded now, but private company that is doing advanced pharmaceutical drug discovery research using AI techniques. And so Recursion Pharmaceuticals is really using AI at the cutting edge of everything they do throughout their drug discovery pipeline. But in particular, they've got a robotic process for collecting and sampling and synthesizing compounds that might be used to treat diseases. And they have pretty advanced microscopy setup where they're looking at pictures of disease cells under microscopes and making calls about, does this drug seem to be impacting positively the disease nature of the cells that we're treating. And so, probably somebody else can give you a multi-hour science lecture on this, but where the AI fits in is they're generating hundreds of thousands or millions of pictures of cells under microscopes all day. That's way more than any human could look at. And what they need is a computer vision based approach to understanding what's working and what's not, and really focus on the cells that are working, where the drugs are working well. They found that by switching to deep learning techniques from kind of classical machine learning techniques for this problem, they were able to go from, say, 80% accuracy to well over 99% accuracy. But that required using a lot more training data than they could realistically process on their kind of existing hardware. And so they've moved from a small, a relatively small on-prem cluster to using cloud cluster to now again with a top 500 supercomputer on-prem running large-scale AI models. And where the machine learning development environment comes in is really helping them effectively leverage that large-scale HPC cluster for these types of problems. And so we're able to speed up their model training by an order of magnitude, as well as provide them features to do things like hyperparameter optimization and so on. And so they've been leveraging the system for several years now, and really, it's become a central kind of piece of their drug discovery workflow, both in a production setting as well as in a research and development setting. And so let's do just kind of in the interest of time, I'll touch briefly on a customer in the autonomous vehicles space that we've been working with. This is one of the large autonomous vehicles companies. They are their key metric of success is, are the vehicles that they're developing safe enough to put on the road without human intervention? All of the companies in this space are pushing towards that same goal. And they are taking a very data-driven approach to how they make their cars more safe. So more examples we can show self-driving cars, the more situations we can model, the safer we can make these vehicles. And they're doing things like building pedestrian detection models and traffic light detection models and so on. And they similarly, because it's such a data-oriented business, and because these models are so computationally demanded, they needed the ability to train these models more quickly, to get them on the car more quickly, so that they can iterate and make these vehicles safer. And so we help them scale beyond, high performance single machines with 8 GPUs in them or 16 GPUs in them in some cases, to in this slide we've got a relatively small cluster indicated, but they're now running at the scale of hundreds of GPUs for single jobs, sometimes even low thousands numbers of GPUs. And that helps them manage the multiple terabytes of new data kind of coming in every day, and continue to make progress on those models. So those are a few live examples, and you can see they're in a variety of industries. Common theme that they all have: advanced AI models, lots of data, and the need to efficiently leverage high performance computing infrastructure in order to get their models trained and out there. And so with that, I'll hand it over to Hoang, who can now show you a live demo of the software environment that we provide each of these customers and many more.
And if anyone has any questions, please feel free to enter them in the Q&A. And we can go through those at the end, or if you'd like, you could raise your hand and we could promote you to ask a question live.
All right, sounds like no additional questions for now. So I'll go ahead and do the demo. So I wanted to show what a user experience looks like when you're using the machine learning development environment that Evan has been speaking of. So in this case, in the interest of time, I'll spend about 10 or so minutes here, and want to make sure we have some time at the end for questions if there are any additional ones, and closing remarks. But for this particular demo, I'd like to use a pedestrian detection model as the use case. So imagine a model developer, you're given access to a machine learning development environment cluster. You have access to a Jupyter notebook that you can run your code in. And you want to develop a computer vision model that can detect pedestrians in images. So without the machine learning development environment, typically what you could do is use your model code, maybe run some scripts that will help you train the model over a certain number of epochs. If you want to do something more advanced, you could write loops in order to help you search through a much larger hyperparameter search space. But all these things are going to be very incremental, and it'll incrementally increase the complexity of the code that you're working with. Similarly, though, if you were to try to scale this out, that would add additional code in the form of infrastructure backend code, as well as changes to the model code itself. If you were to do this without the machine learning development environment, typically that adds a lot of complexity, but that's exactly what the machine learning development environment aims to solve. So if you were to scale this out, the development environment will provide you capabilities to distribute your training. So ensure that you're able to train on hundreds of GPUs if you need to. Include automatic hyperparameter search. So I'll show you in a second what that looks like, but you can search through thousands of different variations of your model in order to find the best one. And then throughout all of these, we have automatic checkpointing and fault tolerance. So you can be assured that a model that potentially could take a month to train, you have intermittent checkpoints taken automatically. So if something happens to the hardware, something happens to your code, you're not going to lose all that work that you've already spent training that model. And from a user experience standpoint, we keep track of all experiment configurations as well. So if you need to, at a later point in time, reproduce or understand how your model was built in order to achieve a certain metric, you can go ahead and go back into the experiment configurations and find that out, or you can continue training using those same configurations, maybe with some modifications in order to improve that model further. All right, so now that we've talked about some of the general benefits, I wanted to show what that looks like to actually start a new experiment on the system. So in the machine learning development environment terminology, an experiment you can think of as an occurrence of model training or a workload. So in this case, we're going to provide two different components. The first is a configuration file, which tells the system what you'd like to do. This particular configuration file will tell the system to train the model on one GPU for a certain period of time. And the second component here is the model code. So in this case, the model code just points to the current directory. And in this current directory, I have my existing model code here. So in order to create the experiment, I go ahead and launch this command, and that creates experiment 282. So what happens is we're taking the model code, taking the configuration, sending that over to the cluster. The cluster will take a look at the configuration, which you can see here. And this configuration will tell the cluster what it is that we'd like to do. So as a user, I'm telling the cluster what it is that I'd like to do here. In this case, I'm telling the cluster to train on a single GPU, slots per trial equals 1, for a length of 2 epochs, and then optimize on this metric that is actually a custom metric that I wrote in my model. Everything else here is also helpful for the training environment. So we include the container that will be used for the training. So as Evan mentioned, everything on the system runs in containers in order to preserve the package and versions in order to preserve that environment that's required in order to train this, as well as reproduce this at a later point in time. And then in this case, the data set comes from S3. This cluster that we're working on is actually a cloud cluster, but very similar work if you're doing it on a local cluster. The data source may come from a file storage solution that you have locally as well. So with that setup, we can go ahead and take a look at what this experiment looks like when it is trained on the cluster. As you can see here, I'm looking at the UI for the cluster. This is where a user would go to in order to monitor and manage their workloads. You'll see that there's a large number of experiments here, but they're also divided by user. So you can imagine if you had, let's say you're supporting specific sets of users, you can have a user over here working on their work, and you can administer this by looking at it from different user perspectives. Additionally, from the cluster standpoint, you can see that we can subdivide the cluster resources into what's called resource pools. So currently I have this divided into a CPU pool, so just CPU only nodes, and a GPU pool, which includes K80 GPUs. You can also have additional pools, maybe for V100s, A100s, and in the future, any additional accelerator that will be supported by the system. So we're looking at supporting heterogeneous accelerators outside of NVIDIA accelerators. So AMD has experimental support as well as other exotic accelerators that are coming onto the market. But with that segmentation, a user could then dictate which pool that they'd want to send their workload to. And this could be an on-premise pool, or it could potentially be a cloud pool for bursting for your workload. So some of our customers have on-premise GPUs. They use that consistently, but when they need to burst, they just send their workload over to a cloud pool. And then that would be what's used in order to run their burst workloads. Looking at the experiment, we can click into it and we'll see that this experiment is currently running. We are logging the metrics that are associated with this experiment. So in this case, we are logging validation average IOU as well as loss. So that's generated from the model training. And then you can also see that we're taking intermittent checkpoints. And this is extremely useful, especially for very large scale model training, because typically these trainings take a very long time. And over that period of time, there could be a variety of issues, either with the hardware or something with the training itself. And you may need to go back and use an existing checkpoint from maybe a few hours ago or maybe a few days ago. This automated system ensures that you don't lose any work along the way. So if you train for 4 weeks, but your model takes an entire 2 months to train, you're not going to lose those 4 weeks of work. You can always just take that checkpoint that was automatically taken from that slightly before the 4-week mark, and then continue training from there. So this is a very useful feature for this type of training, especially the large scale models. And the way that we ensure that when you're continuing from that checkpoint, that you're actually continuing with the right training and the right environment is that we keep track of all this metadata. So metadata, including the image that's used, so you have all the right package as well as the versions, including the data set, and then including the hyperparameters that were used for that particular model training, and then down to the random seed. that's used to initialize the model weights. So all of this information is kept track of and monitored within the system so that the user doesn't have to manually save all of their logs or save all of their model configurations in specific files with different names, which can get very confusing and very difficult to trace at a later point in time. And additionally, you'll see that, of course, we keep track of the logs that are being run, and you can see general log outputs here, as well as the ability to pause and resume the experiment or fork the experiment into something new using the same configuration that we had previously. So all of these capabilities are included as part of the system, and it allows the user to really be interactive with the workloads that they're running, and then be able to train their models appropriately with all of these additional capabilities. One thing I'll point out also here is for the model training itself, we'll look at one that's completed training. This is what the completed training looks like. You'll see that the plots are all set up here. And then you can, of course, also open in TensorBoard to view any additional advanced metrics that's being generated there if you prefer. For the training itself, we also keep track of the metrics that are related to that model. So you can look at throughput, so how many samples are going through the model at any given time per second. You can look at timing metrics, so how quickly some of the functions are running inside the model itself. And that way you can help optimize some of these, as well as the hardware metrics, so system metrics related to the GPU utilization, GPU memory, system memory, disk, network, etc. So all of these things are automatically kept. User doesn't need to write any additional code in order to do so. Everything is managed directly in the cluster itself, and this information is available via our APIs as well if you need to pull that information. All right, so now this experiment has completed training, experiment 282. Let's say, for example, as a user, you wanted to pull the best checkpoint, so whatever was completed training, the best model from there, and then just take a look at how it's performing relative to a test image that you have. So in this case, we'll pull the best checkpoint using the checkpoint APIs, and then take a look at how it does relative to this test image of a few pedestrians walking. And just a heads up, of course, this is done live, so we'll see how this particular training is doing. And as you can see, it is starting to see some objects in here. So this is entirely expected. We've only trained for about 2.5 minutes. So it's seeing some pedestrians here in the image, but it also thinks that some of these cars are pedestrians. So it's getting there, it's moving in the right direction. But let's say, for example, you wanted to distribute this training so you can train it even further. So instead of training on a single GPU, you'd like to distribute this training out and then train it on a larger number of GPUs. And that way it can see more data and then be able to improve faster. So how do you typically do that outside of using the machine learning development environment? Well, you would have to procure the GPUs, set up all the GPUs on the nodes, install the backend software that's required to run that, set up the networking, make sure that you have everything connected and working appropriately, and then also change your model code in order to run this distributed. If you're using the machine learning development environment, we do all of that backend for you automatically. We want the user to be able to just dictate that they want to train on more than one GPU. And the way that they do that is by updating the configuration file. So in the configuration file, you'll notice that instead of slots per trial equals 1, so 1 GPU, like the last training, we just changed this to slots per trial equals 4. And this could be any number depending on how large your cluster is. It could be 64, hundreds, depending on what your cluster is capable of running. But this is the change that you need to make from a user standpoint. And then everything else is taken care of on the back end. Sharding the data, splitting it up into each of the GPUs, managing the training, setting up the backend software, all of that is taken care of. And all I need to do is send that new configuration and then use the same model code in this directory. And I can launch this new experiment using more than one GPU compared to what I did last time. And what's happening here is we're going to start up the experiment. The cluster will see the configuration, realize that it needs 4 GPUs, automatically request that, run all of the installation and setup that's required, and then set up the experiment to run on 4 GPUs. And from the user standpoint, the net result is that now you have a new experiment that's running with 4 GPUs instead of just 1. So this will take a couple minutes to run, but if we take a look at one that's completed a little bit earlier, you'll notice from this perspective, a lot of this information is going to be very similar. It's training, it's getting some results, it's plotting the results, it's taking checkpoints, which is very valuable, especially if you're training over multiple GPUs. So fault tolerance becomes even more valuable at that point. It's keeping track of your configurations. And then from the profiler, you'll see that if we take a look at the GPU information down here, take a second look, there we go. You'll see that there's actually 4 GPUs that are reporting information because we trained this on 4 GPUs. So you'll be able to manage and understand the system metrics for all of those if you're training a distributed training job. So very similarly, as this is continuing to train, what if you wanted to run a more advanced hyperparameter search, right? So you're looking through your model and you realize that you need to search through a lot of different variations and you're trying to find the best one. Well, typically you need to write the code in order to implement some algorithm in order to do that. And then also set up the backend infrastructure, the GPUs, in order to run all of this in parallel. Then save all the results, save all the checkpoints, and then find the best one. With the development environment, you just update the configuration file. So instead of constant values, we're going to use a range. And then we select the algorithm that we'd like to use for this particular setup. In this case, it's adaptive ASHA. Evan had alluded to that earlier. You can consider that principled early stopping. And what that means is we're going to look at the number of variations that you select here. So in this case, we'll look at 24 in total. We're going to train those models with the different variations. And then we're going to intermittently check to see how well they're doing relative to their peers. And if they're doing well, we continue training. And if they're doing poorly, then we stop it early. And with all of that set up, this is managed entirely by the cluster. The logic is already there and it's already implemented. From a user standpoint, you can use this very advanced algorithm just by setting the algorithm name and then changing your parameters so that you're looking through a specific range of values that you'd want to look at. You can launch the experiment the exact same way as before, same model code, and the experiment is going to launch on a series of GPUs depending on what's set in the configuration file. From a user standpoint, you'll see the experiment is being started here. I'll open one that's already completed training to show you what it looks like after it's completed. But this graph here shows what I mean by principled early stopping. You'll see that each of these lines corresponds to one of these different variations of the model, right? And each of these variations, we started off, they have different parameters and we started training them. And at each point, we check and see how well they're doing. And depending on how well they're doing, they either continue training and we'll train them to the end, or we just stop them early and save your resources. As you can tell, the ones that were stopped early, we're doing very poorly in this graph. Higher is better. We're doing very poorly relative to their peers. And at the end, you see there's a few that are very close together that we've trained to the very end. And the rest of them that we stopped early are doing poorly. So you would never really use them at the end anyway. And the advantage of this is it is extremely resource efficient, right? So all of these lines, you can imagine, could have continued training and ended up somewhere here or maybe here. And in those cases, they would result in models that you would never use, but you would still waste all that time and all those GPU resources training. Now, this is 1 GPU per model variation, but imagine if it was 64 GPUs and over a period of a week. So you can see how much GPU hours you'd be saving by using this algorithm and still retrieving the best results out of all of the model variations that you've looked at. So in this case, you'll see that the model, the best model here is a particular trial, 832. And if you look at the hyperparameters, we can see which hyperparameters were used, which values were used in order to generate this model. And of course, everything else is also kept. So checkpointing is kept here, as well as configuration, as well as the hyperparameters. So everything is already saved there automatically for you. And if we look at this particular experiment 281, let's go ahead and check to see what that looks like. So if we were to use the results, essentially the best checkpoint from that experiment, we run it against the same test image, we'll see that it has found a better performing model using different configurations. And now you have not only the trained model with the checkpoint, you also have the configurations that you use in order to train that model. So if you need to reproduce that later or maybe test it against a slightly different configuration, you can do so as well. But this is a significantly better result than what we saw earlier with just a single GPU with just a single set of configurations. So hopefully that clarifies how a user would interact with the system and how they would be able to go from a single GPU to very easily changing a single config line to go to 4 GPUs or any X number of GPUs, and then also be able to go to a large scale hyperparameter search automatically by changing the configuration file alone without having to change any of the model files. To close out, what I want to just show here is the model registry. So let's say, for example, you've gone through the entire process, you have the model that you want, and now you're ready to save that and then start using that model for your downstream serving processes. So we have a built-in model registry on the system, and we can save, let's say from experiment 281, the one we just saw, we want to take the best checkpoint, the best model that was trained and found in there, save it to a model name called pedestrian detection, and then go ahead and register that into the registry. And then what you see here is, if we look at the model registry, there's a model registry entry for pedestrian detection. And the most recent version, version 16, was just registered right now. And of course, you can add additional metadata information about what you were doing for this particular run, but all of that is kept, and all of the checkpointing that's related to that is kept here. And what that means is, whenever you want to retrieve the best performing model from that model name, you can imagine multiple users adding their best versions to this. You can just call by the version, the model name, and then run that inference against whichever images that you want. So you can imagine a more downstream process, just knowing the model name, pedestrian detection, being able to call that, and then all of the teams that are working on that and uploading and managing the models in there, it'll just pull the best performing one and then start using that for any serving capabilities that you're looking for. All right, last thing I'll just note, everything that we're doing here is also supported via our APIs. So we can take a look at the APIs here, but the model creation, experimentation, metrics, all those things can be accessed and managed in an automated fashion if you want to put this into a much larger pipeline or automate the full process. All right, so hopefully that was helpful in demonstrating the user side of things in order to show what it looks like to interact with the machine learning development environment. I'll go ahead and pause here and see if there are any additional questions related to the software itself, or interacting with the software, or any of the capabilities.
Q&A. Anyone who has a question, feel free to enter it in the Q&A, or if you raise your hand, we could promote you to ask it live. And I also see we are approaching the top of the hour here. So
well, thank you, Hoang and Evan, for your presentation. We really appreciate it.
Absolutely.
Yeah, we'll send some follow-ups. This is being recorded, and we'll send that out to folks as well. So again, thank you. Any additional comments or last thoughts before we adjourn here?
Right. Thanks, everyone.
All right. Thanks, everyone. Have a good afternoon.
Right.
Bye now.
Thanks, everyone.